Hello and welcome everyone to the poster debrief on developing an efficient routing heuristic for a drone-assisted delivery problem. My name is Abhishek and I'm a doctoral candidate at the Texas Tech University IMSC department. So today we'll start by introducing a class of related problems. We'll talk about the flying sidekick traveling salesman problem. Then we'll talk about the order first split second heuristic and why this is suited to solving these kind of problems. Then we'll talk about our work, the results that we got, and finally we'll conclude. So to begin, coordinated covering tool problems or CCTP is a class of routing problems that involve multiple vehicles, which can be classified into primary vehicle or secondary vehicles, and they may travel independent of each other. However, they are required to synchronize, which means they're constrained to meet up at certain locations within the network, possibly many times, and presumably due to the autonomy limitations of the secondary vehicle. In the context of last mile and logistics, drone assisted delivery problems or DDP is a subclass within the coordinated covering tool problems in which trucks are assumed to be the primary vehicle and drones are assumed to be the secondary vehicle. Interest in this class of problems by logistic companies has really boosted the research in this field in the last few years. There are several variants of the DDP that may consider multiple number of trucks and multiple number of drones. However, the fundamental case consists only a single truck and a single drone that is capable of delivering up to one package per drone operation. The set of problems are NP hard in nature, but within the basic case, there are two variants of the problem that are commonly studied. The first one is the flying sidekick traveling salesman problem, or the FSTSP, which was developed by Murray and Chu in 2015. And the second one is a traveling salesman problem with drones, or the TSPD problem, which was introduced by Agatz et al. In 2018. Albeit the differences in their complexity and the search space, the objective is to find a heuristic approach that will yield near optimal solutions to a realistically sized problem in reasonable computational time, as there is no means to solve even a medium-sized problem to optimality in polynomial time. Having said that, the order first split second heuristic is one of the commonly used approaches to solve the FSTSP. It was first proposed by Beasley et al. In 1984 to solve the vehicle routing problem. And as indicated in figure 1, it decomposes a routing problem into two iterative steps. The first one involves relaxing the vehicle capacity constraints to construct a giant TSP tour for the vehicle. And then secondly, this tour is optimally partitioned to construct feasible vehicle routing solutions. Beasley noted that the second part of the algorithm can be solved as a shortest path planning algorithm with polynomial time complexity. Moreover, improvements on the solution could be achieved through local searches or perturbations within the routing solution or in the giant tour ordering. There are a few advantages to this approach. Firstly, any routing solution can be represented as a giant tour ordering. Secondly, for any given ordering, the split procedure can be made optimal, even with slight changes to the one proposed by Beasley for broader class of VRP-related problems. And thirdly, efficient local search techniques or perturbations and mutations through meta-heuristics can be developed to improve the routing solutions significantly. The split algorithm, which is the main crux of the heuristic, is such designed to find the optimal solution for a given ordering and is well suited for the flying sidekick traveling salesman problem. Any giant tour ordering represents the truck only TSP route, and within this route, arcs can be constructed to represent a drone operation that involves the launch node, the recovery node, and the drone delivery node. Within a sequence of I to j, in which the ith node is the launch node and jth node is the recovery node, we can have a total of j minus 1 operations. And this is shown in figure 2. And for a given ordering that has n customer locations, we can have a maximum of 1/6 times n plus 1 times n plus 2 times n plus 3 number of arcs. And as a result, the split algorithm has a polynomial complexity. Now, when combined with the ordering part, we search a space of the complexity O(n) factorial to generate the ordering that gives us the optimal solution to the FSTSP in the worst case scenario. As a result, the overall heuristic complexity is at most O(n) factorial n cubed. Evidently, Agatz's EP-all algorithm, which is of the order first split-second approach, is the best algorithm to solve the FSTSP till date. It was published in 2018. They use a dynamic programming-based split algorithm to solve to optimality this solution to a given ordering of nodes. It is O(n) raised to the power 4 complexity and can solve up to instances involving 100 nodes. They furthermore propose a speed up algorithm to their EP algorithm, and this speed up feature reduces the original algorithm to O(n) cubed complexity. However, it misses a certain class of solutions because it misses a certain class of arcs within a given subsequence. The all part represents local searches like 1P, 2P, and 2opt operations that are performed on the giant tour to check for solutions around the local region of the first generated solution. Our split algorithm, which we call the SPP or shortest path planning algorithm, it is to cater to finding the optimal solution to a given ordering of giant tour, and it achieves that with a complexity of O(n) cubed. Although conceptually similar to the EP algorithm, the SPP algorithm has some notable advantages. First, it obtains the optimal solution to an ordered graph in O(n) cubed complexity as compared to the DP-based algorithm proposed by Agatz et al., which does so with a complexity of O(n) to the power 4. And their speedup feature, although is of the same complexity as ours, it misses a certain class of routing solutions. Secondly, our approach allows an efficient implementation of finding the optimal routing solution to an ordered set of customer locations, as it does not need the overhead memory requirements that the DP-based algorithm that was proposed by Agatz et al. Requires for storage, search, and retrieval purposes. These few advantages of the SPP-based split algorithm makes our formulation not only efficient, but also more accurate when compared with the DP-based speed-up feature that was proposed by Agatz et al. In order to compare our split algorithm with theirs, we run both the codes on same 210 instances that were spread across 3 types of distributions and with customer nodes ranging from n equals to 10 to n equals to 200 nodes. Moreover, we keep the same local search strategies to generate the solutions to just compare our split algorithm with theirs. And we see in table 1 that our split algorithm, we observe a mean improvement of 95.38% in computation time and 0.77% in solution quality for SPP all algorithm over the EP all algorithm that was proposed by Agatz et al. Though the EP all and SPP all heuristics may end up exploring the same, exploring different local solution spaces, yet in none of the individual instances, the EP all algorithm can reach a better solution than our SPP all algorithm. On the contrary, further deviation from the departure from the solution quality is indicative of the compounding effect of missing a certain class of solutions. And this is why we see the improvement of 0.77% over the quality. And we do also observe a significant improvement in computational time. Agatz et al. In their publication points out that that it is computationally intractable to solve larger problem sizes, that is more than 100 node instances. However, using the SPP-all algorithm, we can easily solve problems with 250 node instances in less than 2 minutes. We claim this is due to the efficient implementation of the SPP-based split algorithm in addition to the overhead efficiency of the algorithm. To furthermore assess the solution quality of the heuristic, we compared the mean performance of the EP-all and the SPP-all heuristic for 10 node instances to the optimal solution for the FSTSP that is generated using our MILP formulation. The results are presented in table 2. There are a total of 30 instances divided across the same 3 distribution types, and each classification has got 10 instances. Both the EP-all and SPP-all heuristics perform relatively well for the 10 node instances, with a reported average optimality gap of just a little more than 1% for both cases. And of the 30 instances, the SPP-all can reach the optimal FSTSP solution for 63.3% of the cases. However, the Agatz et al.'s EP-all reaches it for 57% of the total number of instances. And the double center instances perform the best for both the algorithms. The promising results that we obtain here, that we just presented, with the simplest case of drone-assisted delivery problem, makes us believe that it can be extended to other problems that lie within the same umbrella. The area of investigation lies in developing efficient split algorithms that are preferably polynomial in nature, and also further developing approaches to the reorderings of the giant tour following the split approach. A common problem that we face with standard local search strategies is that the final solution tends to get trapped within a local optima that depends on the initial solution. Smart implementation will ensure more search space is covered, and this will ensure that we can get solutions that are globally optimal, or at least closer to the global optima. The work on it is underway. With this, I conclude my presentation on our SPP-based order first split second heuristic. I thank you all for joining and see you guys later. Thank you.